Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, part of the great stuff. This is the AAS Journal Author Series, and I am super happy to have Akshatha Vydula with us today. Hello, Akshatha.
Hi, Frank. It's great to be on the series.
Well, it's very nice of you to be talking about your very lovely AJ article, which we'll get to here in a minute. And Akshatha, where are you located at?
Tempe, Arizona.
Uh-oh, home team. Uh-oh, alert. Well, I don't have to ask you how the weather is because it's a little rainy outside on this January 25th, 2024 as we record this. So very cool. And Akshata, what's your position there at in Tempe at ASU?
So I'm currently a fourth year PhD student at the School of Earth and Space Exploration, Arizona State. And I mostly do work on radio astronomy, but I do also fiddle with a little bit of other things.
Very cool. Very cool. Well, I look forward to stop too very soon. So very and you mentioned a little bit, you want to talk a little bit more about what kind of research you like to do?
Yeah, so I kind of go kind of on the extremes of the scales of the universe. And by that, what I mean is for the most time, I'm mostly doing early cosmology and epoch of reionization. And during the summers, I have affiliation with the Los Alamos National Laboratory, where I work a little bit on measuring neutron lifetime by using Moon as our test bed, using planetary science techniques and very old lunar prospector data. And I do say very old because the data is teeny tiny bit older than me. It was recorded back. Yeah. Yeah, it was
it
recorded
simply
back
must be old.
Yeah. But yeah, it was recorded back in the January of 1998, and I was born in August of 1998. So it's a little bit older than me.
It's a
And
birthday
that's
present. It's a
probably,
birthday.
yeah. Yeah, so I kind of do work on neutrons, which, relatively speaking, on the smaller size scales, and also early universe and ionization bubbles of epoch of ionization, which is on the bigger scales of the universe.
Cool. I like the dynamic range there. Very nice. Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. Go grab a copy, get one for free, get it. Low frequency radio recombination lines away from the inner galactic plane. And Akshata, take us away.
Yes, so this is a paper that came out very recently. It was, in fact, to me, felt like it was a Christmas present getting this paper out, because I had been working on this since the beginning of my grad school. But I don't think this paper would have been possible without any of the co-authors, and especially my advisor, Judd Bowman, who has kind of helped me walk through every step of analysis, getting the reverse report and whatnot, and also just kind of generally getting into the idea of publishing, which is great. So yeah, I'm very thankful for this first paper that came out very recently.
Congratulations.
Thank you. So in this paper, we do study a little bit about radio recombination lines, which by definition, they're technically recombination lines. And by that, what I mean is if you have an electron at different energy levels, and if they're jumping up or down an energy level, they kind of emit a certain radiation. And that is kind of that difference in energy is what leads to the recombination line. And we call them radio recombination lines because these happen within the frequency range of radio frequencies, and it also is because they happen at like much lower frequencies, less than 200 megahertz. Most of the studies that have come out about radio recombination lines, they're fairly at higher frequencies, about a gigahertz or so. And so we want to do this. We want to do this at a much lower frequency ranges.
Okay. All right.
So the frequencies of these radio recombination lines are actually governed by equation 1, which I think is on page page 4.
Yeah. And Radio recombination lines. There we go. Yes.
It's on page 4, equation 1. And I just wanted to highlight that equation where we kind of show that N1 and N2, which are principal quantum numbers. And when I say electrons are jumping up and down in energy level, these are the principal quantum numbers that I'm talking about. And so depending on which energy level or which principal quantum numbers these electrons are making transition, we kind of get these lines at that frequency that are determined by these principal quantum numbers. And it's kind of interesting to note here that obviously there's a slight dependence on the atom that you're looking at and the size of the atom and what kind of electron or what kind of energy levels that you're looking at. But more importantly, these N1 and N2 have to be really, really high for the recombination lines to happen within the radio frequency ranges.
Okay.
And so we'll look at it in a minute, but then these are much, by bigger, I mean the size of the atoms is extremely big. We're talking like principal quantum numbers like 400 or 500, okay. Even 600. So the atoms have to be like extremely large in size, where the electrons are at much, much higher principal quantum numbers.
Yes.
Okay. And so, which makes it very interesting because these are also rare to see. Okay, so now we can go back to the introduction, just now that we have the sense of scale of how big the atom is and what kind of frequency ranges that we are talking about.
Okay, I'm with you.
So most of introduction is kind of giving the literature survey of the kind of studies that have happened with low frequency radio recombination lines. And like I mentioned, these are sort of hard to study just because of how faint they are and how lower frequencies that we are interested in. And so the kind of papers that we were looking at, they were kind of limited, but although there have been, some really good work that's been done, but we are more interested in the diffuse radio recombination lines. And by that, what I mean is generally radio recombination lines can come they can come from different sources. They could be coming from star-forming H2 regions. They could be coming from planetary nebulas, and they could also be coming from diffuse radio from the diffuse sources. By that, what I mean is the gases are like colder and they're lower density molecular clouds, and generally they also are from along the galactic plane. And we'll know more about as we go through the paper. But these are generally coming from along the galactic plane. And generally speaking, these are they're very faint. By that, what I mean is 0.01 to 0.1% of the background continuum, which also makes it, which also makes it, which also makes it really hard to observe. But this is nearly not as faint as the signal that my thesis is mostly focused on, which is the signal coming from the epoch of ionization, which is 10 to the -4 or -5 of the background continuum. And at these frequencies, we are generally are only able to observe carbon and hydrogen lines just because they have lower ionization potential compared to any of the other, let's say, like helium lines or.
Sure.
So, which is why this paper kind of focuses on low frequency carbon and hydrogen lines.
Okay.
And so now we can go back to figure 1, I guess. Where I show, or before that, I can also kind of give a little bit about how we get these data.
Okay.
So that should be in the observation section. So this, so the data that we've collected for this comes from EDGES, which is Experiment to Detect Global Epoch of Ionization Signal. And this is a single dipole antenna that's deployed in the remote deserts of Western Australia. And the primary objective of this telescope is to observe the early universe, the global 21 centimeter signal, as we call it, which is essentially coming from when the first stars and galaxies started forming right after Big Bang, maybe about 300,000 years after Big Bang. So this is extremely high redshift, and it could be as high as like one of the detections we had back in 2018, which the studies, like some of the sections in this paper are kind of based off of the detection in 2018.
Yes.
And so we had a detection of the global 21 centimeter signal at the redshift of 17, and the line center was about 78 megahertz.
Okay.
Again, low frequencies.
Okay.
And so we take the data from the same experiment, which was one of the primary reasons of doing this experiment, of doing this observation. We primarily had like 2 or 3 different objectives. One of them was like, well, we are doing this global 21 centimeter signal. We wanted to see what are the other science that we can do with this existing instrument.
Yeah.
And recombination lines was one of the obvious candidates, given that there hasn't been all that much work done at low frequencies, which is interesting because at these low frequencies, the science cases are kind of limited to like high redshift science and whatnot. And so instrumentation and getting the systematics lower is also very, very difficult. Given that we have this instrument, it was kind of like a low-hanging fruit to kind of do this low frequency recombination line studies. The second one is that we want to see, given that there was a detection in 2018, which obviously had a lot of discussion after the detection, because the claims of the detection was that the amplitude of the signal was twice as higher than the theoretical models, and it was twice as big, and so it didn't really agree with the models that were established at the time. But now we have other models that do explain the detection, that could be either because of excess dark matter and whatnot. So the second objective of doing this study was also that we want to see if certain radio recombination lines, when stacked against each other, could lead to something that could cause this extra detection or extra amplitude extra absorption feature. Okay. And so that was another, I guess, seeing if radio recombination lines could be systematics to the global 21 centimeter signal. Right. So for a lot of people interested in studying these diffuse radio recombination lines, this is like great science. But for us, it's like, we don't want this. So let's see if we find it. And if we do, let's flag them. So that was the second objective. And obviously the third objective was that we also, as we were writing this paper, we also realized that there hasn't been all that much study on how the amplitude of recombination line changes as a function of frequency. So would you have a deeper absorption line or a deeper carbon absorption at lower frequency versus higher frequency? Or would you have, and the same goes with hydrogen as well. Yeah. And so these were kind of primary reasons of why we were doing this observations, even though our group, as you can see from the co-authors, we are all primarily interested in cosmic dawn and epoch ionization and radio instrumentation and whatnot. So this is kind of like a secondary science for us. So which also may have been another reason why this was a paper in making for a little over 2 years.
Yeah. Good quality.
So
okay.
Yeah. So now if you go to the figure 1, which is where I show, right there. So the first panel in that figure is calibrated spectra that we get from a typical EDGES data. And it's interesting also because this is an example of one of the days of the data. And in this paper, we use about 385 days of data. So like I said, it's a very faint measurement, so we need a lot of integration time. And so this is an example of one of the day. And the second panel in that is after we kind of subtract a polynomial from that spectra, and that's the residuals that we are left with. And so if you look at the amplitude in the first panel of the figure, those are extremely high brightness temperature values, which is the synchrotron emission and whatnot. So like if you take out, if you fit a polynomial and take it out, you're left with residuals, which are kind of this 1 or 2 Kelvin sort of range of values. But you kind of still have these broadband structures, which is not great, right? Like you don't want those broadband structures. And so that's when we take out a 5-term polynomial, but you can keep on increasing these polynomials, right? And so the third panel is where I'm showing if you take out like an eight-parter or 8-term polynomial subtracted from that initial spectra, you are almost kind of left with these Gaussian type residuals.
Right.
And the other interesting thing is also that the amplitude of these Gaussian type residuals is higher at lower frequencies than it is at lower.
Yes, it is.
So which also is because as you from the first panel, the synchrotron emission is also higher at lower frequencies than it is at lower frequencies, at higher frequencies. The other interesting thing that I would like to highlight is in the second and third panel, there are vertical red lines, those red faint lines.
Yes.
And those red faint lines are the predicted or not predicted, are the actual frequencies at which we expect to see these radio recombination lines. And those frequencies are governed by the equation 1 that I showed in the first 5 minutes. And so the other interesting thing here is also that at lower frequency, if you like really zoom into this panel, at really low frequencies, those vertical red lines are closer together than they are at higher frequencies. So that's
gotcha.
So that's saying that inverse square proportionality with the principal quantum numbers.
Yes.
And so all of these lines are alpha lines, alpha carbon lines, which means the delta n, n1 minus n2 or n2 minus n1 is 1. And so these are also at really high principal quantum numbers. And this is actually one of the things that will come in handy for the next couple of figures, where we show that. So basically, if you so there are about 85 or 86 lines in that 50 to 87 megahertz range. And so if you go to the next figure, you can see figure 2.
Sorry.
So if you go to the figure 2, we take.
There we go.
Yeah. We take one of the lines. So from figure 1, we have those vertical lines.
Right.
So if we really zoom into one of those vertical lines, and then kind of cut off everything else, so that was like 50 to 87 megahertz. Now you can see this relative frequency on the x-axis on the lower panel, or on it's the same x-axis. But anyways, if you really look at one of the lines and then cut out everything else, zoom into the 300 kilohertz window of that one line, you can see in the first panel, you can kind of see that absorption sort of feature, but it's barely visible because it's so sensitive that it's hard to see, right? Like in the first panel, you kind of like, if you ask someone like, okay, do you see an absorption profile? Maybe not. It's hard to say, right?
Yeah.
But if we take all of those 85 or 86 windows, stack them.
Yeah.
And then average them, that's when you get a really high confident detection of recombination lines. Except that this is representative of the entire band and not a single line.
Yes.
So for the first panel, for example, I can say the first panel is like a single recombination line.
Right.
The second panel is the average of 50 to 87 megahertz. So that kind of comes down to the effective frequency of 66.1 megahertz. So in our entire band, we essentially see one recombination line after stacking all of them.
Cool.
And in the figure caption, you can see that there's 85 recombination lines, and the principal quantum numbers start from 423, go all the way to 507. So the atom is massive, right? So that's why it's diffuse recombination lines, lower density, because when the atoms are that big, it's difficult to get denser gas.
Yeah, because they destroy themselves if it gets too dense.
Yeah. And so this is where we kind of see, for example, this is the carbon alpha line. And so this is our 28 sigma detection after stacking, which is to me is quite cool. That's the signal to noise, right? Like you never know unless you kind of just stack them, average them. That's the answer to pretty much everything in astronomy. Just stack and average them, you get your signal to noise.
Cool. Very cool. Okay.
So
that's a detection.
So the other, yeah. So the other thing we also do is the edges is the way edges works is it's a single dipole, and so the beam of the antenna is extremely big. Yeah. For example, if a typical radio astronomy textbook, you can see that the antenna, if you want to look at a certain source, you're sort of seeing how good the resolution is based off of how big the dish is, right? Yes. Bigger the dish, better the resolution. Oh, yeah. The interesting thing about edges is that we are looking at global 21 centimeter signal, which means we don't want to look at a particular source. We want to look at all sky at all time. Yeah. Which is why our beam cannot resolve any sources. Our beam is about 75 degrees wide. So at any given point of time, you're pretty much seeing the entire sky, like as an average signal, right. Which also means that you cannot know where the lines are. Like you cannot kind of say, like the lines are coming from particular. Yeah, exactly. And so instead what we do is we observe 24 hours and we divide them into 2 hours chunks. Okay. So which is what we call the local LST binning, local sidereal time binning. So we have 12 LST bins in 24 hours. And for 384 days, we stack. So we basically divide every day into 12 LST bins. And we try to find these recombination lines in each of those 12 LST bins that are averaged over 384 days. And so if you go down to the next figure, that's where I show.
Okay, let's do that. Here's our stacking. There's our stack. Let's do a global here and we'll zoom in if need be.
Yes.
Okay, stacked.
And so, so this is the 12 LST bins that are all binned into 24 hours of data. Okay. This is our way of, I guess like more or less kind of trying to find out where these lines are coming from.
Yeah, it's intensive direct.
Yeah, so it's so the way I guess it's kind of intuitive if you know what you're looking at, which is in a 24-hour cycle, you have the galactic plane that comes in and out of the beam, right? So the galactic plane is coming in at LST 18, which is if you do convert it, that's that galactic hour angle 0, which is LST 18. That's when the galactic center is right overhead at the zenith. And then the galaxy is moving out of the plane, and then you kind of reach these LST4, LST2, LST6. The galactic plane is below the horizon. You don't see it anymore. Right. And then it comes back up, and then it comes, LST14, 15, 16 comes back up in the beam. Right. Now, if you really look at it, the recombination lines are stronger when the galactic plane is overhead, versus it's almost impossible to detect them when the galactic plane is not overhead, it's below the horizon. Which tells us that these recombination lines that we are seeing are coming from the galactic plane, which is why the title of the paper is low frequency radio recombination lines from the galactic plane. So that was a roundabout way of basically finding out where these lines are coming from. And so we have fairly confident detection, and these are carbon alpha lines. And the blue lines on this figure is basically the average the average that we get, or the stacked average that we get from our data. The orange one is a double Gaussian fit to these lines. And the reason, the reason why we do a double Gaussian fit is because turns out that these are carbon absorption lines. Hydrogen emission lines are only about 35 kilohertz below the carbon absorption lines. And so And so when we saw the double hump profile there, we're
Yep.
like, okay, let's find out if these are hydrogen emission lines. And turns out those are hydrogen emission lines, which is why we do like a combined fit of hydrogen emission and carbon absorption lines.
Got it.
And so we repeat this for carbon beta lines and hydrogen beta lines. And by beta, what I mean is that N1 and N2 delta is now 2. And so if you scroll down to the next page, figure 4 is what gives you, it gives you
there.
There. Yeah. There. Yeah. So that's carbon beta. Yeah. And turns out carbon beta is much harder to observe than carbon alpha, just because these are much fainter lines, right? And they're rarer and they're harder to find out. And even here, you kind of see a little bit of that hump where you expect hydrogen beta, but there isn't a lot of confidence in fitting those. It's harder to find. It's harder to fit for those parameters just because of how noisy it is and how harder it is to detect. And we also actually detect carbon gamma lines. If you scroll down to the next figure, that's where you see carbon gamma lines. And
second, I just want to get the amplitudes here. Okay, and then this one.
Yeah. Okay.
Larger.
I was going to talk about amplitude.
The amplitudes are larger in the alpha.
Yeah.
Opposed to the beta.
Yeah, I was going to talk about the amplitudes after I showed the carbon gamma lines.
Okay. I just. Okay. Gamma.
Yeah. Sorry.
Profiles.
Yeah. So these are gamma lines. These are much harder to find, and the 2 panels here. So the way I showed those 12 panels for carbon alpha and carbon beta lines. For carbon gamma lines, these 2 panels are pretty much representative of everything else, which is why we say on the galactic plane, off the galactic plane. And we don't kind of bother to, show the 12 panels because they're more or less the same.
Right.
And so now if you go back up to the table, which is where I show the amplitudes of these lines.
Okay, table 1.
Yes.
Yes.
And so here you can kind of see that carbon alpha and carbon beta lines. Generally, these are about 4 times. So carbon alpha is generally about 4 times stronger than carbon beta lines. And this is also something that's been seen in a paper by Erickson et al. 1995. And they show that relative, the ratio of carbon alpha to beta to gamma. And our results are pretty spot on with what they see, which is always a great confirmation of what we're doing, given that this instrument wasn't. So again, you can see that LSD-18 for carbon alpha has the highest amplitude, and then as you go down to the LSD-4 or 6, the amplitude are kind of lower, and that trend kind of still holds for carbon beta and alpha or hydrogen alpha lines.
Yes.
Yeah. So the other thing that you can see in this I guess in this table is also full width half max of these lines, which kind of tells us how big or like how wide these lines are. Generally speaking, these are about 24, 22, 25 kilohertz-ish wide. And something that I guess we talk a little bit about this in the paper is that a lot of these lines are kind of, they get stretched out because of Doppler effects and because so Doppler broadening. So there are multiple ways because of Earth's rotation around the relative motion, and there's also line broadening because of hot gas, cold gas, whether the lines are coming from hot or cold gas, etc. So generally these are about 20 to 25 kilohertz wide.
Yes.
Which also means that your frequency resolution should be very, very low to be able to see these.
Right.
To be able to see these lines. We were kind of cutting close with our frequency resolution, our frequency resolution was 12 kilohertz, I think,
Okay.
or 12 kilohertz.
Yep.
So 6.1 kilohertz, but then we apply Blackman-Harris window, so that's 12.2 kilohertz. And so these are still maybe a channel or two wide signals, which is also saying that if you were to do this similar observation, one of the things that you should kind of consider is very low frequency resolution in your observations.
Yes.
Okay, so this is pretty much everything about the detection of these lines.
Cool.
The next thing, like I said, was I guess seeing the next figures that are in the paper that are more just kind of reiterating the fact that these are coming from the Galactic Center. So, for example,
Gamma.
yeah.
So model
if you
tracer.
go down, yeah.
Model
Right.
tracer. Okay.
So if you go, yeah. So this is the model tracer section where we talk about if you were to correlate these lines with the Planck CO map or even the this is the Planck CO map. So here you can see that if this is a correlation of the simulated recombination lines with the Planck CO map, and so you can see that these are relatively higher at the LSTs that we expect recombination lines, and not so much at the LSTs that we don't.
Okay.
Which is also similar to the next plot, which is where we see the Haslam map, which is very dearly used by a lot of radio astronomers. So this is the Haslam map at 408 megahertz, kind of down to extrapolated down to lower frequencies. Again, in that correlation, you can see that the amplitudes are higher, and you can see the galactic plane at LSTs that we do want to look, that we are interested in, or the LSTs where we see lines, and not so much in the LSTs that we don't.
Right.
And so the next figure is again another reiteration of I guess like a different representation of how we see this. So these are peak normalized in each of these correlations. One of them, so the red dots there are hydrogen alpha lines, hydrogen emission lines.
Okay.
The purple ones are carbon alpha absorption lines, and then and then we have the green dotted and dashed line, which is the recombination lines, proxy as for the Planck CO map, and also the simulated and observed continuum on black and blue dots.
Okay.
All of them very, very, they agree pretty nicely that these are all coming from the galactic center, and so the amplitudes are lower off the galactic center and higher on the galactic center. So the next section is pretty simple, which is we repeat all of this for higher, for midband, for edges midbands. Edges operates in low band, midband, and high band. So the first good chunk of the paper was analysis on the low band, which is 50 to 87 megahertz, and midband, because we had data lying around, so why not?
Why not?
I mean, we started as why not, and turns out that was pretty important part of the
Sometimes
next piece of puzzle that we,
Sometimes you have to ask.
And so we kind of repeat the whole exercise for midband, which is 108 to 124 megahertz. And again, the results are consistent in that. But the other important thing is that if you look at the amplitudes of these signals, so if you go back up to figure 9, right there, these amplitudes. Now, if you see the hydrogen emission lines is stronger than carbon absorption line.
Yes, right here. Yep.
Which is actually, we started thinking about why is hydrogen emission line stronger at these higher frequencies compared to lower frequencies. Turns out that these lines kind of have a transition. So if you go down to the next section, which is where we talk about the frequency dependence of recombination lines, which is what I was mentioning as one of the objectives of doing this study, where we want to see how recombination line or how the amplitude of the recombination lines change as a function of frequencies. I will not go into the details of model fitting, but we can look at the figure. I think that gives a better picture than looking at those numbers.
Yeah, what equation was that? 7.
So the right above that, right there, yeah, equation 7.
Yeah,
that's the equation we use to model the amplitude of recombination lines.
Yeah.
And so this has a dependence for optical depth, that's tau L. And so we do this modeling within the local thermodynamic equilibrium, where it assumes that B and beta n, which is these are the factors that we use in basically modeling the amplitude of the radio recombination lines. Cool. And so within the LTE conditions, we assume that Bn and beta n are 1. And so at that point, it's just, that equation boils down to TE minus TR
basically
times times the optical depth. And TE there is the electron temperature, and TR is the background radiation temperature.
Okay.
So you have an emission line when the electron temperature is higher than the background radiation temperature, an absorption line when the opposite. And so we do this within the LTE conditions for carbon alpha and carbon beta. So if you scroll down to the figure, I think that figure gives a better view of these, like all of this mathy model fitting that we do in this page that kind of gives that pictorially in this picture. So this is carbon alpha and carbon beta modeling. So the blue, like the light blue lines or the dots are the low band results that we have from edges. And the mid band is with that green line. We only have 1 point there. Right there at 120 something.
There it is, right there.
Yeah, it's hidden right. It's hidden right there. And we looked at a few of the other past, observations at these low frequencies. And like I mentioned, it's harder to find these lines at low frequencies, but we did find 2 papers, and you can see by that the frequencies of it. Ericsson 1995, and there was nothing until 2019.
Wow.
And so these are very hard to see. And so we do a model fitting considering every point that we have in low band, and we add the lines coming from the 2019 paper and the 1995 paper, all of them as like a single data point. And then we fit that equation 7 into this. And so here we see the best fit on the strong priors and relaxed priors. And in strong priors, we kind of, we let everything kind of fix based off of the physical processes that we expect, except for one parameter, which is spectral index. And then we do the similar thing for relaxed priors, where we let all the parameters kind of free float and get to wherever they want to go. And then the last kind of fit there is including B and beta n, which is another way of saying that's a non-LTE fit.
Correct.
Yeah. So we do this for LSD18, which is where we see the recombination lines. And then we also do this at LSD 0 to 12, all of them integrated, which is off the galactic bin. And the reason why we do 12-hour LSD bin instead of 2 hours is because this gives us better sensitivity.
Right.
And so we do this similarly also to carbon beta lines. And again, you can see that the LTE fits are pretty, they're well behaved within those frequency ranges. The other interesting thing this plot also shows is that zero crossing on the y-axis. So that zero crossing is exactly in the top panel where the LSD18 is. So that zero crossing is where the lines go from absorption to emission. And so for carbon lines, you can see that this zero crossing happens at about 140 megahertz, which is why our carbon absorption lines were stronger at lower frequencies than in our mid-band. So because it's closer to that transition of getting into emission line.
Cool.
Which is also, that's also consistent with carbon beta lines, which is what we also see in our mid-band, is that those amplitudes are lower at midband. So if you scroll down to hydrogen line, this is another interesting plot. So that's the next figure in the paper, which is where we show the similar model fitting for hydrogen lines.
Okay.
Again, so these are all like low band, mid band, and we don't have any data from the Ericsson 1995 at these frequencies, but we do have a couple of data points from the 2019 paper by the EDA team. And here we kind of, again, do the similar model fitting, but turns out that this has a better agreement with the non-LTE fit.
Okay.
Which means that you cannot ignore, you cannot consider, basically you cannot consider ignore these B and beta N coefficients in doing these model fits. And here the zero crossing happens at much lower frequencies. So in that top panel, you can see that zero crossing happens at, like pretty much at the beginning of our band. We started at 50 megahertz. This is at the beginning of the band. And so the interesting part here is also that this data agrees with the 2019 paper, except that there is, it's predicted, again, I guess this model shows that transition happens at 50 megahertz, but we don't have confirmation of whether or not this does actually happen. Which is very interesting, because our lowest point here goes down to 66 megahertz after averaging. So this is kind of, obviously the thing that came out of the paper, but turns out that this is the most important part of the paper.
Hooray.
Because, because we see these transitions pretty clearly given our frequency ranges. So now going to the actual objective that we thought of doing, in this paper, which is studying the recombination lines and their effects. And again, this table gives these model parameters
for LTE and non-LTE.
But for LTE and non-LTE models. So LTE does pretty well for carbon lines, but non-LTE does great for hydrogen alpha lines.
Sure. Okay, cool. We get into
so here we see how are these recombination lines affecting the global and power spectrum.
I can see why this was the original. Yeah, I can see why this was the original motivation, and took a little track. Okay, I'm with you.
Yes. And so what we essentially do to study this is we take those initial double Gaussian model fits from carbon, hydrogen, all of these lines that we see, and we take a simulated sky spectrum that is coming from edges, for example, and we artificially inject these lines within the edges data.
Okay.
Yes, we artificially inject them, and then we try to model them out, and then see, so basically we do this in two different ways. In case one, you have the sky spectrum and an artificially injected global 21 centimeter signal. And in case two, you have sky spectrum, artificially injected global 21 centimeter signal, and recombination lines.
Gotcha.
And so we try to retrieve the 21 centimeter signal back, and then we want to see the difference between with and without the recombination lines, and how much of an effect that has on the actual signal retrieval of the global 21 centimeter signal.
Excellent. I'm with you. Very good. Okay.
So in this figure, you can see that the top panel is the residuals after removing a polynomial model, and then we inject the frequency-dependent carbon absorption line, which is the deeper lines, the frequency-dependent carbon beta lines, which is lower amplitude, like in the top panel. So you can see basically the bigger amplitudes are carbon alpha lines, smaller amplitudes are carbon beta lines, and the emission lines are our hydrogen lines.
Okay. Yes.
And then this also has the global 21 centimeter signal. And we do note that we don't inject a 500 millikelvin signal, which is what was the detected signal from 2018. We do more, models that agree with theoretical, the other traditional models, which is 200 millikelvin.
Okay.
So we inject a 200 millikelvin global 21 centimeter signal. And then the second panel is basically after frequency rebinning. So like I mentioned, our frequency resolution for doing this kind of science has to be 6.1 kilohertz, or like anything lower than 25 kilohertz, we're able to see these signals.
Yes.
But for global 21 centimeter signal, we don't need that kind of frequency resolution. And the 2018 paper actually did have a frequency resolution of 390 kilohertz, which is way, way, way higher than this one. And so we rebin it to 390 kilohertz. And so here you can see the only difference between panel 1 and panel 2 here is that the frequency rebinning, and even that actually reduces your residuals by that much because you're averaging by those many channels.
Gotcha. Cool.
And so the final plot there is the residuals after basically after modeling everything out. The blue one is with the recombination lines, and the orange one is without the recombination lines.
Okay. Good.
And then if you want to look at the numbers, turns out that recombination lines are not that big of an effect, because the difference between with and without the recombination lines in the signal retrieved is only about a few millikelvin, 2 or 3 millikelvin, which isn't that bad, because we are looking at a signal that's 200 millikelvin. So that's like less than 1 or 2% effect, which is great. And so it turns out, we're fine. We don't have to flag them as of yet.
Right.
And so now we repeat the same exercise, just because, again, why not?
We're already here.
A power spectrum. Yeah, with the power spectrum experiment, like HERA, for example, hydrogen epochronization array, which is also an experiment to study the early universe, cosmic dawn, except that this kind of looks at the power spectrum coming from a particular point in sky, as opposed to a global sky average signal. And then again, in this figure, we do the similar line insertion and whatnot. I guess better than this figure is the next figure that shows the better picture of what really is happening. So yeah, right this here. So again, the blue and orange one are again with and without the recombination lines. This is what we call the delay spectrum, which is you take do a Fourier transform and kind of see what kind of noise levels that you're at. Turns out that recombination lines do add about 10 to the negative 2 to the noise floor, but this is way below the detection profile, or the typical detection levels that you'd expect for the 21 centimeter or the power spectrum 21 centimeter.
Cool.
So I guess the big takeaway from this paper is that as of right now, all of these experiments that are looking at making detections of the global 21 centimeter signal or the power spectrum 21 centimeter signal, they do not have any immediate, I guess, because right now they're all in the detection phase, right? They're all still trying to detect, and all of these are still trying to achieve the sensitivity that is required for an experiment like this. And so we are kind of hidden in this thick battle against getting rid of those systematics and achieving those sensitivity. So as of right now, our sources of systematics are bigger, and they're not recombination lines. But that said, in a decade or so, when these experiments move away from the detection phase to a characterization phase, where you're not just detecting, but also trying to map out which part of the sky is this coming from, or doing a much more involved studies on the 21 centimeter redshifted 21 centimeter signal, that's when recombination lines become something that we'd have to think about. And we'd have to think about how we are flagging them, how we are detecting them, how we are getting rid of them in our experiments.
Cool.
So for all the radio astronomers out there that are trying to do 21 centimeter redshifted 21 centimeter analysis, do not worry about recombination lab as of yet, because right now it's a 2% effect. But when we get down to, when we get down and into like much smaller systematics, that's when we'd have to think about them.
Cool. Very nice. Beautiful. Beautiful, beautiful.
Yep.
Akshata, I want to thank you so much for walking us through your very awesome first AJ paper. Congratulations.
Yeah, thank you.
And you touched on it a little bit here, particularly toward the end. Ooh, what happened there? But I'm curious, where do you think we go from here, given this published article? Are there additional radio recombination lines that might be of interest? Are any experiments at the point where the 2% effect from the radio recombination lines will be important? Are those ongoing? Are they just started? Just sort of next steps, where do we go from here?
Yeah, I think this is a very exciting time to be for low frequency experiments, not just radio recombination lines, because we have SKA coming out. We have a lot of lunar observatories coming up that have much wider science goals, including the redshifted 21 centimeter signal. So recombination lines have, I think, they have a lot of potential to understand not just the galactic plane, but also if you have higher resolution, spatial resolution, more, I guess, understanding of where they're coming from, kind of what kind of information they have of the gaseous region that they're coming from. But more interestingly, in the near-term future, I guess the near-term goals or things that we would want to look forward to is that so the line crossing that I showed, the zero crossing that I showed,
Yes.
Because of these new and upcoming telescopes, we are very much closer to be able to actually see those line crossing. So we can see exactly where that line crossing happens in emission and absorption, which I think will tell us a lot about our interstellar medium and ionizing bubbles and whatnot.
Yes. Very cool. Very nice. Very nice. Well, I really look forward to seeing this develop over the next couple of years. It'll be very exciting.
Yeah.
This
didn't. Sorry, I am not someone who does radio recombination lines, not before this paper at least. But being able to work on this and writing this paper has now made me super excited about radio recombination lines. And now I think, like, even if there's like a new somebody publishes something about sensitivity in low frequency instruments, I'm like, can we do radio recombination lines with this?
Yes. Good.
Yeah, so this has been a great experience working on this data.
It's going to be an awesome chapter or chapters in your thesis. That'll be great.
Yeah.
Awesome.
Yeah.
All right. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.